So hello everybody. I'm really pleased to give a webinar to you today, and I hope that that we'll be having a good time together. Do we still have the same time as was planned, or will we have less time?
No, we have the same time.
Okay, very good. So yeah, originally I'm from Germany. I've lived there for 27 years, and then went from there to the United States, first to Texas, where I did my PhD. And then 20 years ago, I came to California, and I'm a professor here at the University of California in Davis and an air quality specialist. And that means I study the impact animal agriculture has on air and climate. And I quantify those impacts, and I find ways to mitigate the impacts through feeding, through husbandry, through all different kinds of angles. And that also includes, of course, manure management. Today, I will talk to you about one gas, namely methane, which is really a very important greenhouse gas and the main greenhouse gas coming from animal agriculture. Why methane? Why do I talk about methane? I talk about methane because a lot of the nuance around methane has not really been understood up until recently, and that has had serious consequences on how we choose public policy and how we regulate farms and how we talk to farmers about their impact. And so I think it's really important for us to get this right. So I have produced a YouTube video called Rethinking Methane. So you get this for free if you go, if you just Google Rethinking Methane and YouTube, you get it. It's a little 5-minute video that explains much of what I'm about to talk about. So I will skip a couple of slides here and go to this one here. By the way, Maria, please feel free to make my slides into PDFs and share it with all attendees. So let me start with this slide here. This slide shows the sun radiating solar beams to the surface of the Earth, and normally that radiation would be reflected back into space. If there weren't these so-called greenhouse gases, gases such as carbon dioxide, methane, nitrous oxide, effectively form a shield, or let's call it a blanket, over our Earth's atmosphere, retaining some of that solar heat back in our atmosphere. And this function is very important. Without these greenhouse gases, life on Earth would be too cold and we couldn't live here. So we need greenhouse gases, but the problem is we have produced too many of those, and that means the blanket, figuratively speaking, has become too thick. While most climate scientists will say that the most important greenhouse gas is CO2, which is produced when we burn oil, coal, and gas, which are fossil fuels, the critics of animal agriculture say, no, we should really concentrate on methane. Why? Because methane is more potent in trapping heat from the sun than CO2. And that's true, it is more potent. But as you can see in the next couple of slides, there's more to it. Another greenhouse gas of great interest is nitrous oxide. As you can see, it's not the one that's produced in greatest amounts, but it has a high potency. It's very heat trapping. Okay. So when I say heat trapping, what that means is, just imagine you were to try to keep your coffee warm, let's say in the morning. You can put this coffee into a styrofoam cup, or you can put it into a china cup like this, or you can put it into a Starbucks insulated cup like this. And we all know the coffee stays warm different length of time, depending upon what beverage container you choose. Now, the styrofoam cup coffee cools down the fastest, and the Starbucks cup keeps it warm the longest. Now, the same is true for these greenhouse gases, CO2, methane, and nitrous oxide. CO2, while it is the most abundant greenhouse gas out there, other than water, CO2 does not trap the heat very well, and so it has the lowest global warming potential. That's what it's called. Nitrous oxide has, among these three, or across these three listed here, the highest global warming potential, and methane lies in between. What this means is that CO2, when it traps the heat from the sun, traps it, but not for very long. Methane, 28 times better than CO2, and nitrous oxide, 265 times better or more than CO2. And so this is where the focus on methane comes from, that we assign such a high factor to it. This global warming potential, or GWP 100, is a matrix that was generated in the 1990s. When the negotiation for the Kyoto Climate Accord were generated, to help policymakers figuring out which sector of society produces what kind of warming and so on. And scientists put these factors up, and underneath the table was a long list of footnotes qualifying and cautioning about its news. But in the years following, those footnotes were cut off, and only these three factors prevailed. They changed slightly since, but overall, methane sources are quantified by using this GWP 100. Now, GWP 100 is called that because it describes the warming potential over 100 years. Now, methane does not have a lifespan of 100 years. And as you can see in a minute, this matrix called GWP 100 has issues with it. But it has been the issue everybody has been using for decades. And everybody is using that still. So I've had issues with it, and I have mentioned them throughout the years. And I see that I have an increasing following now of people agreeing that there are challenges around the use of GWP 100. Why is methane so different from other greenhouse gases, such as CO2 or nitrous oxide? Well, one of the main reasons is that methane is not just produced, but methane is also destroyed. In other words, there is a budget for methane. On the left side of this slide, you see various sources of methane, including fossil fuel production, agriculture and waste, biomass burning, and so on. All of these sources combined produce a total of almost 560 teragrams globally. So 560 teragrams of methane are produced, but as you can see on the right side, 550 teragrams of methane are being destroyed. In other words, this gas has a budget. It's not just produced, it's also destroyed. And if you want to know the net, then you have to subtract the one from the other. And then you arrive what's encircled in this red box here. That is the net, a number we still seek to reduce, but certainly a number very different compared to just looking at the sources alone. And that is what largely happens in the media, that people only look at sources. But for methane, it's important to understand there are sinks. And if you look at this large arrow pointing down and the very large number, 515, then you see underneath it says sink from chemical reactions in the atmosphere. So what are these chemical reactions in the atmosphere that take out methane? There's a process called oxidation. To be precise, it's called hydroxyl oxidation. And hydroxyl oxidation pretty much kills methane and converts it back to where it came from. In the case of biogenic methane, methane from livestock, that methane, the carbon in the methane, came from originally from atmospheric CO2. And when it's destroyed, when that biogenic methane is destroyed, it goes back to that atmospheric CO2. So, and this takes on average a little over a decade. So methane is not just produced, but methane is also destroyed. Hydroxyl oxidation is the name of the process, and it makes this a very important part of the narrative. So that's the take-home message from this slide. It leads to what I'm depicting on this slide, a great difference across these gases with respect to the half-life, how long they are in the atmosphere. As you can see, CO2 stays in the atmosphere for a very long time, 1,000 years or longer. Nitrous oxide, another long-lived climate pollutant, stays in the atmosphere for over 100 years. But methane is not a long-lived climate pollutant. Methane is a short-lived climate pollutant with a lifespan or a half-life of 12 years. And so this is really important when it comes to characterizing how these gases warm our planet. And let's not forget, this is what it's all about. We care about greenhouse gases only for one reason, And that reason is that they warm our planet. Shouldn't we have ways to characterizing the warming impact of the beef, of the dairy, of other sectors? I think so. But this GWP 100 matrix I showed you before does not express the impact of a gas on warming, but it simply gives you what's called CO2 equivalent emissions. For example, if you were to have a dairy or a beef operation and you produce, let's say, 10 tons of methane, then what you have to do is multiply this factor with the 10 tons that your farm emits, and then you get 280 tons of CO2e, CO2 equivalent emissions. So that's how these factors are used, okay? So if you produce 10 tons of methane, 10 times 28 equals 280. If you produce 10 tons of nitrous oxide, then you multiply that with this higher factor. That is how GWP 100 characterizes methane and nitrous oxide as CO2e, CO2 equivalent emissions. Okay, so if you have any clarification questions or so, feel free to ask. Okay, I'm happy to interrupt and clarify anything that you want to know. So I will briefly now talk about where the carbon that's in the methane, where that carbon originates. In the case of biogenic methane, which is the methane from natural sources such as cattle, the carbon in the CH4, the C in the CH4, comes out of the atmosphere. So imagine CO2 being in the atmosphere during photosynthesis. The plants our animals eat, whether it's grasses or a mixed ration, a TMR, these plants during their lifetime took carbon out of the air during photosynthesis. You know, they need sunlight, water, and a source of carbon. They get that carbon from the atmosphere. They assimilate that in the plant material and convert it into carbohydrates, such as cellulose and starch. Our animals eat that cellulose and starch, and then in their rumen produce some of that methane that's then belched out through the mouth, or that's produced from their manure. But, ladies and gentlemen, is this carbon, the C in the methane, is that new and additional carbon added to the atmosphere? Or is it not new and additional? The answer is it's not new and additional because it was in the atmosphere before, but in a different form, in the form of CO2. So that does not mean that this methane doesn't matter, but it means that this carbon is not new and additional. If you have, and this is important, if you have a constant number of livestock, let's say in Slovenia, you used to have, I'm just making up numbers now, I have no idea about Slovenian livestock numbers, but let's just say you used to have 1 million ruminants in 1980. And in 2000, you still had 1 million. And in 2020, you still have 1 million. Then that means the constant cattle number during those years would have generated a constant amount of methane. And the reason why it's constant and not increasing is because methane is not just produced, but also destroyed. And if you have a constant source of methane, then you have a constant source of warming. No additional warming from constant cattle herds or constant ruminant herds. Where does that methane go? Well, I already told you, a process occurs. It's called hydroxyl oxidation that kills the methane and make it back into CO2. So the carbon in the biogenic carbon cycle goes around and around and around and is relatively short-lived. While that carbon is in the form of methane, it traps heat. If it's a constant source of methane, then it causes constant warming, but no additional warming. So this is really important. Now the question is, so why do I keep stressing this issue of constant carbon and constant warming? Because the Paris Climate Accord that we have all signed on to has as a goal a warming goal of not adding additional 2 degrees centigrade to the world's atmosphere. That's the goal, not to reduce human carbon by so and so many million metric tons, but to prevent additional warming. So the question we now have for the beef sector, the dairy sector, and other livestock sectors in our respective countries is, how do we get to a point where our livestock sector does not add additional warming, so that we can abide by the Paris Climate Accord. And that's what I'm about to talk to you about. Now, are other sources of greenhouse gases, such as the use of oil, coal, and gas that generates CO2, are they also cyclical like the biogenic carbon cycle? Well, let's look at the main one. The main one is, so what generates CO2 by and large is the use of fossil fuels. And fossil fuels are oil, coal, and gas that used to be hundreds of millions of years, animals and plants, such as dinosaurs and trees and so on. These animals and plants died, decayed, and fossilized, and they accumulated underground for hundreds of millions of years until last 70 years, 70 that is, 70 years ago, humans started to extract those fossil fuels, and we burned that carbon with cars, trucks, trains, planes, ships, and so on. And every time we burn that fossil fuel, we add new and additional carbon to the atmosphere. This is not a short-lived carbon cycle, but this is carbon that accumulated underground for hundreds of millions of years, that's extracted during a short time span, and then burned, adding new additional carbon to the atmosphere. This is not even close to being the same as the biogenic carbon cycle. I contrast these two on this slide. The fossil fuel carbon was in the ground for so long, we took it out, we burned it, and now this ancient carbon is added to the atmosphere. While on the other side, the biogenic carbon cycle, we have atmospheric CO2 making it into plants in the form of carbon, into plants, being made into cellulose. Some of that carbon stays above ground, but the majority of the CO2 carbon goes below ground into the roots of these plants. And from there, soil microbes take that carbon, and a process occurs called soil carbon sequestration. A very important tool in our fight against climate change is to have healthy soils that help us trap carbon that was in the air, now in the soil. About 1/3 of all anthropogenic carbon, so carbon that we released into the atmosphere, is now stored in our soils. And it's very important to manage these soils well to keep the carbon there. Now, our animals eat some of the above ground vegetation, and when they do, they produce some methane. The methane is belched out, but converted back into CO2 within 10 years, 10 to 12 years. So this is a short-lived cycle on the right side. This is a one-way street on the left side. What I just said does not mean that this methane here doesn't matter. It does matter, but what it means is, on the left side, you always add new and additional carbon, and that causes new and additional warming. And on the right side, as long as the cattle herds are constant, you are generating constant warming. And it goes around from CO2 to carbohydrates, to methane, to CO2, to carbohydrates, and so on. So a very different principle behind these two. So I will now talk to you about the difference between two important gases. The one is CO2, and the other one is methane. And I will talk about the differences in how these gases warm our planet. Imagine you were to work 20 kilometers away from home, and you drive on Monday, day one. You drive your car and you burn gas, and then you put CO2 into the atmosphere. On Tuesday, you drive again, same distance, and you add new and additional carbon to the existing stock from the previous day. On Wednesday, you drive again, and on Thursday, and on Friday, and every time you drive your car, you add new and additional carbon to the existing stock from the previous day, previous days, previous week, previous month, previous decade, and so on. In other words, CO2 is a stock gas. CO2 accumulates in the atmosphere. Every time we burn fossil fuel, we put new and additional carbon into the atmosphere. And that causes new and additional warming. Now, currently, methane is treated in most countries as if it were to accumulate just like CO2, as if every time our cows belch or the manure produces methane, This were new and additional carbon added to the atmosphere. What this quantification leaves out is the fact that methane is not just produced, but methane is also destroyed. And that, ladies and gentlemen, makes methane not a stock gas, but a flow gas. If you have a constant source of methane, you have a constant source of warming, because this gas is not just produced, this gas is also destroyed. I will now give you an analogy. I hope it's clear enough. An analogy, one for CO2 and how that warms the planet, and the second one for methane and how methane warms the planet. And so I use a bathtub analogy. Imagine you having a bathtub and it has a faucet, but no drain. A faucet, but no drain. If you turn on the faucet on low, medium, or high, water will go into your bathtub and the water levels will rise. They can never go down because there's no drain. Now comes the other analogy, the one for methane. Here you have a bathtub with both a faucet, but also a drain, and the drain is always open. If you now turn the faucet on normal, you put water into the bathtub, but an equal amount is going out through the drain. As a result, the water level stays stable. If you turn down the faucet, then you add fewer water to the bathtub than you let go of through the drain. And as a result, water levels can go down. Meaning if we mitigate methane, we can reduce warming. Okay, very important. Only if you take this faucet and you turn it on all the way, you might add more water to this bathtub than you let go of through the drain. And in that case, even though the drain is open, water levels will rise. So this is really an important analogy because it tells you that the fact that methane is not just produced, but also destroyed has a different impact on warming compared to what's going on with CO2. Okay, this is really important. Colleagues of ours from Oxford University in the United Kingdom criticized the fact that the use of this GWP 100 that I alluded to before does not really consider the atmospheric removal of methane appropriately. And they said years ago that this one is the right bullet point here, that this GWP 100 overestimates the impact of methane, of constant methane sources on warming by a factor of 4. And they said that this GWP 100 really overlooks what's happening when you reduce methane, namely that you also reduce warming. They developed a new matrix called GWP star, and this GWP star accounts for the impact of methane on warming, accounting for the atmospheric removal and not just the production of this gas. So I want to show you in a direct comparison what happens when you look at 3 scenarios, first with this GWP 100 and then with the GWP star, how they predict 3 different scenarios very differently. The first scenario is one where over 30 years, we significantly increase methane. The second one is one, we call it a stable scenario, where over 30 years, we slightly reduce methane by 10% over 30 years. And the third one is one where we strongly reduce methane by 35%. How would this increase, the stable and the decreasing scenario of methane be depicted using this old matrix GWP 100? Again, that's the matrix the world has been using up until today. How would this old unit characterize the increasing, the stable, and the decreasing methane? In both cases, it would say that we are adding a lot of additional CO2 equivalent emissions. Even in the second and the third scenario, it does say that. We know that's wrong because methane is not a stock gas, it's a flow gas. So if we now look at the GWP star, the new matrix from Oxford, then a very different picture comes up. Namely, that yes, if you increase methane, you add a lot of additional warming. This is the blue north of the x-axis. If you add methane, you add additional warming. But what happens if you slightly reduce methane to warming? Well, in that case, you don't see any blue north of the x-axis, but because of the slight reduction, you see a negative sign in front of the number. And the blue is now south of the x-axis, and that means negative warming. Negative warming is a fancy word for cooling. meaning if you reduce methane, you reduce warming and you pull carbon from the atmosphere. If you reduce methane by a lot, let's say 35%, then you're pulling a large amount of warming from our atmosphere. And that shows that if we have the capacity of reducing this gas, we will have a short-term impact on climate. And because methane is the main greenhouse gas in animal agriculture is a natural sector within society to make use of mitigation and have an impact on climate. So the question is, can we in agriculture be part of a climate solution? And the answer lies in front of us. Yes, we can. If we reduce methane, and if we reduce it by a lot, we are pulling carbon from the atmosphere, much as if we were to plant forests, which do the same thing. So remember what this looks like. A strong reduction by 35% reduces a lot of warming. So before I go any further, the notion that I presented on this slide here, that GWP 100 drastically overstates the impact of constant sources of methane on warming, was recently confirmed in the most recent Intergovernmental Panel for Climate Change report that came out last year in the AR6 version. In it, it said, and I quote, expressing methane emissions as CO2 equivalent emissions using GWP 100 overstates the effect of constant methane emissions on temperatures by a factor of 3 to 4. So what we have been saying for years has now found its way into the IPCC AR6 report. And you will notice a GWP star is quoted throughout this document over and over and over again. It's now a recognized way of characterizing methane's impact on warming. And I think rightfully so. It's a very important new development. And what this also says here, this highlighted thing, is that what we have done for the last 30 years throughout the world, using this old matrix for methane and not accounting for the removal, has significant relevance to agriculture, has significant relevance to public policy. So now, can it be done that we reduce methane by a lot? Let's say 30 or 40%. In California, where I live, we have a new law, and that new law mandates a 40% reduction of methane, 40% reduction of methane by the year 2030. So in 8 years from now, 7 years from now, we have to produce 40% less methane than we did in the year 2013. So the question is, can this be done? And the answer is, it likely can be done if the government and if the different agencies in a given locality work with farmers. In the case of California, our legislature decided to make methane reduction something that people want to do through investment help. So dairies, you see here a dairy on the bottom right, a dairy with 1,500 cows. That's the average size in California, milking cows. They used to have an open lagoon where the manure was stored. Now that lagoon is covered. They're called anaerobic digesters. I know that you have those in Slovenia. They're all over Europe, but in Europe they look more like tanks. They are covered, and the biomass is kept under anaerobic conditions where microbes produce biogas. This is something similar, but at a larger scale. These covered lagoons produce biogas. You see it bulging out this plastic here. And this biogas contains 60% methane. This methane is really pure energy, okay? You could burn it and make it into power, or you can convert it and make it into fuels to replace diesel. And that's exactly what we do in California. We are covering lagoons. We are trapping the biogas. We are then converting the biogas into transportation fuels for semi-trucks, for buses, and so on. And once it's in those semi-trucks and buses, we replace diesel. And that looks like this here, where you take dairy, renewable natural gas, that's the name of this biogas that's cleaned up, and we get it from there into our semi-trucks, replacing diesel. This, ladies and gentlemen, is what we call here in the United States a double whammy. Double whammy because you reduce emissions on the farm and you reduce emissions on the road, and farmers make money by doing so. So the state of California decided to go what I call the carrot approach of using incentives, financial incentives, to reduce emissions. Other places in the world use the cane approach of rules and regulations and fines, maybe taxes, to force farmers to reduce emissions. Everybody on the call who is a parent who has kids at home knows that the carrot approach works much better than the cane approach. It might not be surprising to you that it works the same way with farmers. If you work with them and not against them, then they will make things happen. These reductions that I talked about earlier, those 40% reductions that the legislature has set forward to our dairy, beef, and other sectors, will be achieved by the state working with the farmers and not against them. It's not just manure reduction, it's also feed additives. You see a couple of them listed here. We have done research here at UC Davis looking at the use of seaweed, fatty acids, 3-NOP, oregano, and other things, and how much they can reduce methane. We have found that reductions are possible anywhere between 10 to 30, 40% from belching. Okay, so these feed additives are or have been developed in order to reduce enteric emissions, meaning the emissions, the methane that's belched out. I have recently, last 2 weeks, traveled Finland and Ireland, Germany, and Scotland, and I learned during those visits that there are now also genetic approaches. There are now approaches of genetically selecting low methane cows. There are ways to predict whether an animal produces a lot of methane or not. And you can now select for low methane cows. The New Zealanders have developed a bolus approach, which is something you put into the animal's rumen, and it slowly releases an active ingredient that inhibits the formation of methane. And the New Zealanders are also working on a vaccine that you can put into the animal, and that vaccine has supposedly an impact on methane. So there are different approaches, okay? Some of them related to manure, some of them are related to enteric emissions. And I'm very bullish to believe, or when I say that I believe that in the next 5 years, our farmers here in this country, but also throughout Europe and throughout the world, will have many more tools available to reduce methane. And I do believe that methane reduction goals will pop up all over the world. They're already here. In the US, they are in certain parts of Europe. I think they will spread out all over Europe. And they will not be the only environmental issue that will be that will have to be resolved. Others are nitrogen, particularly in Europe. But throughout this talk today, I focus on methane. So we started late. Okay, so I should be okay with time. I want to change a little bit the focus and give you a little bit of an idea as to some other challenges that we are dealing with. Here's a global one. It's called the 2050 challenge. The 2050 challenge is depicted on this slide, showing the year 1750 to the year 2050, hence the name 2050 challenge. You see here human population over time. And I'm a little over 50. When I was a little boy, we were right here at 3 billion people. Today, we are at 8 billion people. And by the time I'm an old man, we'll be at 9.5 billion people. In other words, ladies and gentlemen, throughout my lifetime, human population on this planet will have tripled. We'll have 3 times more people on this planet throughout my lifetime. But we will not have 3 times more natural resources to feed all these people. And that makes it mandatory, that makes it imperative that we find better ways of producing food, that we find what the best efficiencies are to grow food, because if we don't, we will have many people who will not have food. What's interesting on this slide too is that the developed world is kind of plateauing population-wise, whereas the developing world is increasing. And this is not largely a function of everybody having way more babies than in the past, but it's mainly a function of increasing life expectancies. So in many countries of the world where people only grew to be 50 or 60 in the past, they are now dying age 70 or 80. And cumulatively, that has a big impact on human population. One of the favorite slides that I have here is this. It shows the world and a circle over Southeast Asia. And this circle here contains more people in it than the rest of the world combined. More people live inside the circle than outside the circle. And so it clearly shows you there's a hotspot for food security in the years to come. But it's not the only one. The other one is Africa. While human population in Southeast Asia will increase by over 40%, Africa will increase human population by half. And the Americas are relatively stable. Europe will slightly shrink human population-wise by the year 2050. We have two hotspots, Asia and Africa. But while we have this tripling of human population in our lifetime, we have limitations. And what you see on this slide here in color is one of these limitations. What you see in color here are the only areas in the world with arable land, meaning with land where you can grow crops for people or for animals, where you can grow crops. That doesn't mean that is all the agricultural land. In fact, there is a lot additional agricultural land, but in fact, 2/3 more of this land that you see here is agricultural land that's not depicted on this slide, but it's there. But what it is rangeland. It's marginal land that cannot be used to grow crops, but it can be used to graze animals. And that's because what grows there is cellulose. The only animals that can digest cellulose are ruminants. And because of those ruminant animals, we can make use of a lot more land than you see on this slide. Those people, and I see that discussion a lot in Europe, who say, let's get rid of animal agriculture, would effectively get rid of 2/3 of all agricultural land in the world that's currently used by ruminants. Ruminants are a very important contributor to global food security. This slide here shows on the x-axis milk output per cow per year. So from low producing cows on the left side to high producing cows on the right side. And the y-axis here shows the greenhouse gas output per unit of fat and protein corrected milk. What this slide shows effectively are many little diamonds. Each diamond is one country in the world. And it shows that there are many countries that have very little milk production per cow per year. And those countries with very little milk production per cow per year have a very high carbon footprint. So these could be countries like India, many African countries, many Asian countries, and so on. They're the ones on the left side. You can see that the more productive a cow becomes, the lower is the relative carbon footprint. So in many countries that are quite efficient in producing milk, we see they have a relatively low carbon footprint. Those with low efficiencies have high carbon footprints. What I'm telling you here is that production efficiencies and emission intensities are inversely related. Production efficiencies and emission intensities are inversely related. When you're more productive, you produce relatively fewer emissions per unit of milk produced. The same is true for meat and so on. The slide from the FAO in Rome shows on the x-axis different countries or regions in the world. On the y-axis, the carbon footprint per unit of milk produced. And again, you see that there's a large spread throughout the world in the carbon footprint of milk production. And so there are some hotspots, and you see them here. And these are the same hotspots that I showed before with respect to human population increase. The same areas where human population is going through the roof are also the ones with the greatest issues around efficiencies in food production and resulting emissions in total. The FAO, the Food and Agriculture Organization, and the IPCC, the Intergovernmental Panel for Climate Change, estimate that 70 to 80% of the global livestock emissions occur in developing countries. Okay, 70 to 80% of global livestock emissions occur in developing countries. So, for example, India and Brazil, these two countries, have more cattle in it than the rest of the world combined. Okay, for these countries to get the environmental story right is very, very important for world average livestock emissions. It's not that the other countries don't matter, but these countries matter in particular because there are so many animals and so many of them are very inefficient. So what can be done to reduce environmental footprint of livestock? There are four main themes. The one is to improve reproduction, then to improve the animal health, to vaccinate and or treat animals, and to improve genetics, as well as feeding more energy-dense diets. So reproduction, veterinary care, genetics, and nutrition are the four main tools that have helped us in many developed countries of the world to decrease the number of animals needed to produce a given amount of product to historic lows. Never before has the environmental footprint of livestock production in most developed countries been lower than it is today. And it continues to go this route. Just an example here of the US, we used to have 25 million dairy cows in the United States back in 1950. Today, we no longer have 25, we now have 9 million. So we have gone down from 25 to 9, pretty drastic decrease. But with this much smaller herd today, we are producing 60% more milk than we used to. So we went from 25 to 9, but we are producing 60% more milk with this much smaller herd. And that means that the carbon footprint and environmental footprint in general has gone down by 2/3 over that period of time. Here you see 1 billion kilograms of milk produced in 1944 versus 2007. And you see here how much lower the requirements to producing that 1 billion kilogram of milk was in 2007 versus in 1944. So the improvements in reproduction, in nutrition, in genetics, and in feeding have led to a drastic reduction of the environmental footprint of our dairy herd. The same is true for the poultry herd, the same is true for the beef herd, and so on. So now I get this question here all the time, and I just want to mention it briefly. Can we eat our way out of climate change? There are companies like this one here who promise the world that if we eat more of these alternatives to beef and pork and so on, that this has a huge impact on the carbon footprint. But does it? Well, colleagues of mine studied it, and they looked at, for example, what it would take if somebody like myself, who's an omnivore, I eat everything, plants, animals, and so on, if I were to say, I go to the most extreme form and not eat any animal source foods, I become vegan for 1 year. If I were to do that, I would reduce my carbon footprint by 0.8 tons of greenhouse gases. So you will ask, is that a lot or not a lot? Well, last week I came back from Europe, and this one flight per one passenger generated 1.6 tons of greenhouse gases. So I would have to go vegan for 2 years to offset this one flight that I did to Europe per passenger. It's not likely going to happen, by the way, but that's just from a mathematical perspective, what would have to happen if I were to try to compensate for this flight. And it gives you an idea as to how important or unimportant those contributions are. If the entire United States were to go meatless Monday, we would reduce our entire carbon footprint in this country by 0.3%. And an entire US going vegan, and believe me, that will never happen, but just for math purposes, would reduce the carbon footprint of this country by 2.6%. So that's just to give you an idea. Does our food system have no impact on the environment? No, definitely, I'm not saying that. It does have an impact. But would a moderate change of our eating habits have a big impact on climate? I don't think so. Now, first of all, I want to tell you, while I'm citing vegan things here, I have no problem with people being vegan. If they want to be vegan, they can be vegan. I will never criticize that. But the reason why I bring this up here is because oftentimes I now see in the media that this veganism is touted as a new gold standard of sorts, okay? If you want to protect the climate, be a vegan. If you want to save your health from disease, be a vegan, and so on. And so I've done some look into this, and I cannot confirm any of that. In fact, not too long ago, I was contacted by somebody, by a leader within the Vegan Society of the United States. And we talked about all kinds of things. And toward the end of our discussion, I asked him what the greatest challenge is to his association, the Vegan Society of the United States. And he said, Frank, without a doubt, our biggest challenge is the retention rate. And I said, well, what does that mean? And he said, of all the people who go vegetarian and vegan, after 1 year, 84 revert back to what they used to be before. And this statistic shows this year. So of the people in the United States that have tried this, the smallest minority stays with it. So 84% of all vegetarians and vegans in this country who have tried it for a year revert back to what they were before. And I said to him, if this were true, then that would mean for every one vegan who's active today, there are 5 former vegetarians and vegans. And he said, yes. And I said, well, why is that? These people are quite dedicated in being vegans and vegetarians. Why would they go back? And he had no answer. So I don't know what it is. Is it a lack of taste? Is it a lack of nutrition? I don't know what the reason is, but is it a gold standard? I don't think so. If it were a gold standard, people would not leave it in droves. If you want to know what the biggest challenge of our food system is on the environment, it's depicted on this slide. It's a US family, average US family, in front of all the food that's wasted every year. About 40%, 40, of all the food produced in the United States today goes to waste. And you might think, well, that's the US, they're crazy. Well, the same is true in Europe. Most European countries have similar numbers. About 40% of all food produced in the entire developed world goes to waste. And even in developing countries, so much food goes to waste, but there they call it food loss because it doesn't occur so much at the consumer levels like it does in the developed world. So that means in our households and restaurants, but in the developing world, it happens more at the producer level because they can't harvest on time or transport the goods to the markets and so on. It is a global problem of food waste and food loss that we need to deal with. And it's not to say that we shouldn't reduce emissions in agriculture. We should. And I'm very clear about this. My whole research deals with ways to reduce emissions. But to say that we have to end animal agriculture for climate is ridiculous. We don't have to do that. We can work with our farmers to make meaningful reductions of greenhouse gases. If we do it in the case of methane, then these reductions of methane reduce warming, and our livestock sector can become climate neutral. And this can happen in a relatively short time frame. But for that to happen, we have to work with them and not against them. So with that, if you're not on Twitter, I am on Twitter. GHG Guru is my handle. I encourage you to join me. We're having a lot of fun on there. My center, the center I'm directing, the UC Davis Clear Center, is on Twitter. I'm writing a blog. You find it under this address here. And my center, the Clear Center, is also on the internet. Of course, we have a web page, which is very active with all kinds of explainers and blogs and YouTubes and so on, explaining some of those very complex, sometimes confusing issues that are often discussed in the public. And with that, I thank you very much for your attention, and I'm very happy to entertain any questions that you have.
Thank you very much, Professor Frank Mitloehner. I'm sure that our participants have questions. I think it's already some questions in the chat. Yeah, Alesh Pfister asked, does any policy take into account the emissions from the reduction of organic carbon in arable soils since the beginning of more aggressive soil cultivation?
So I first have to clarify, I'm not a soil expert at all, and I don't really deal with soils. Soils are extremely important, and there's a lot of research going on in this field of soil management and carbon sequestration and so on. Unfortunately, currently, in most places in the world, farmers get zero credit for soil carbon sequestration. In most places in the world, the impact of soil carbon sequestration has not really been studied. And policymakers are not really giving farmers credit at this point. In all the places I know of, I have not seen a single place in the world where a farmer who is doing a good job on reducing carbon losses and maximizing carbon storage, where they would have gotten any kind of incentive payment. I have not seen it. I hope this will change because farmers have this amazing tool and we should appreciate that.
Okay. Rok Mihalic from Biotechnical Faculty asked, do you know what is seaweed that it's so effective as feed additive for methane emissions reductions?
Yes, I do know that. So there are two feed additives. One is called seaweed. The Latin term is Asparagopsis taxiformis. It's a tropical seaweed. It doesn't grow in Europe. It grows in Australia and New Zealand. And this seaweed Asparagopsis contains an active ingredient called bromoflor or bromoform. And this active ingredient inhibits the enzymatic production of methane in the rumen. And it does that very effectively. The same actually is also happening with a chemical called 3-NOP. The commercial name is Bovaer. It's now available in Europe to be purchased and fed to animals. So both of these additives, seaweed and Bovaer, do the same thing. There's a 9-step enzymatic production of methane in the rumen of cattle, and it disrupts the last step. And by disrupting it, methane is not formed. The problem with seaweed is that this chemical that does it, the bromoform, is a carcinogen. And when it breaks down in the cow, it's broken down into bromine and iodine, and both of them are toxins. So the question is, do we find concentrations of seaweed that are low enough so that these toxins don't build up? Because any kind of toxicological issue will be the kiss of death of seaweed, you can imagine. The other issue around seaweed is that it impacts palatability. Cattle oftentimes don't like it. They approach the feed bunk, they smell the seaweed, and they eat less. And that, of course, is a big problem too. I have heard that certain scientists have overcome that challenge, but there are still challenges around seaweed, okay? There are still challenges. But seaweed is very effective in reducing enteric methane, as is Bovaer, this DSM product sold in Europe. It comes from a Dutch-Swiss company, DSM. These things reduce methane by 30–40%, and so they are effective. There are other additives that don't disrupt the methane generation the way that Bovaer and seaweed does, but they change the microbial composition in the rumen, so essential oils and tannins and so on. So in the next 5 years, we will have additives that reduce enteric emissions. Right now, they are more in the experimental stage.
Professor Jože Verbič from Agriculture Institute asked, how does the non-agriculture public in the United States feel about the new findings on the warming effect of methane? When might the new approach be adopted by the IPCC for reporting?
So I start with the second part of the question. If you go to the IPCC AR6 report that I quoted before, you will find the GWP star is already in there. The IPCC does not prescribe one way or another of accounting. The IPCC only tells countries, pick which one is best for you, and then tell the world what you picked, and then you go with it. So what I'm not saying is let's get rid of GWP 100. Why not? Because the whole world has been using it and is used to it. So we can't just say we forget it. But I would say account using GWP 100 and in parallel also GWP star. And then do your accounting both ways. The GWP star is way more scientific, is actually a unit or a matrix that tells you how methane from a sector, let's say the dairy sector or the beef sector in Slovenia, affects the climate. How your beef and dairy herd affect the climate. That's what GWP star does, how it affects the warming. It can be used in order to tell your producers at what point in the future they can be climate neutral. They no longer add additional warming. And it can be used to help you producers to learn how to get to this point. What kind of mitigation is needed to get to this point? GWP star can do that. GWP 100 can never do that. So I'm proposing the use of both in parallel. Okay. So that's the second part of this question. The first one, how does the non-agricultural public feel about new findings? It depends on what part of the non-agricultural public. The general public, non-agricultural, is, well, they don't really care very much about methane, and they don't really hear much about this. And I'm sure it's the same in Slovenia. But those who are interested, they are happy that we now know more than we did 5 or 10 years ago. But there are also people in the non-agricultural public who hate what I just told you, because they just hate animal agriculture. And they don't want things to go better. They want animal agriculture to go out, to end, to stop, because they have beliefs that we should not use animals for any kind of human activities, not as pets, not as companion animals, not as food animals, not as zoo animals. They just want to stop it. And those people are very critical of anything that looks like progress. I'm telling you this. I think that we should be very proud of what we have achieved in animal agriculture, in agriculture overall. The progress we have made over the last few decades has been immense, incredibly important, and we will continue to make progress. But agriculture cannot do this alone. Just like the health sector cannot do it alone, preventing the next pandemic or whatever next outbreak there might be, our farmers need support. And if they get that, they will find solutions to those most pressing issues we have.
Thank you. Simon asked, how do you see cattle facilities in the future? Eventually closed, completely closed? Are experimental facilities already there?
So I do not think that cattle facilities will be closed. I see a huge demand for animal source foods. This demand is not going down, it's going up. And I do see that many of the plant-based alternatives that are so often touted in the media are struggling really badly. Here in the United States, all of the plant-based alternative companies, except for one, but all of the others have gone down, 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 and down over the last 2 years. So much so that they are struggling to survive. At the same time, the demand for animal source foods has gone up. Even though the base is so much higher than that of plant-based alternatives, the demand has gone up further for animal source foods. So the question is not one of, will animal facilities close? The question is, how will we produce, what kind of drivers will there be? Animal welfare, climate, nitrogen, workers, and so on. Things are developing. They're not static, they're developing. Objectives are changing, and our farmers will adopt. They always have adopted to new developments, and they will continue to do that. Now, are there experimental facilities? Absolutely there are, and some of them look really awesome. I've visited some facilities in the Netherlands, for example, some poultry facilities and others, and I feel, wow, they are really listening to people's concerns. I do think that that agricultural production has challenges. There are some even that have problems. But instead of saying, because some of them have problems, we need to end agriculture or animal agriculture, it's ridiculous. Those who have problems need to work on their problems and solve them. It's not rocket science. That's just the way it is and always has been and will continue to be. So I'm very positive about what I see in agriculture. I am hopeful that the public policy sector will understand how strategically important agriculture is. No farmers, no food.
Aleš Pfister asks, can you say something regarding the difference in greenhouse gas emissions between raising livestock in ranch land versus feedlots? Thank you.
Yeah, so feedlots mean something else in different parts of the world. So here in the United States, our feedlots are animals that are concentrated in relatively small areas, and all the feed is brought in from the outside, right? That's a feedlot. And I know in Europe, feedlots do the same thing. They don't grow, the animals are not grazing, in other words, but they're eating diets that are high in concentrates. And so because of that, animals grow very fast, are normally finished in feedlots during a short period of time, several months. And that very fast period oftentimes reduces their total lifespan quite a lot. So here in the United States, for example, an animal, all beef cattle are on pasture for about 2/3 of their lives. All animals are on pasture for 2/3 of their lives, beef cattle. Those that are grass finished, they stay on pasture until they go to slaughter. And they go to slaughter when they're 26 to 30 months of age. So close to 3 years, 2.5, 3 years. Their feedlot finished peers, they start on pasture, but they spend the last 4 months of their life in a feedlot. And they go to slaughter when they're 14 to 16 months of age. So the feedlot finished animals are almost half the age of the grass finished animals. And this shorter lifespan has an impact on lifelong emissions that come from these animals. You can imagine they live almost half the length of time. It has an impact on how much they eat, how much they drink, how much they belch, how much manure they produce, and so on. What affects the carbon footprint the most, the impact of these animals on greenhouse gases, is the amount of roughage these animals eat, because it is the roughage in the rumen that's converted by rumen microbes into methane. So roughage, another word for that is fiber. The more pasture animals eat, the higher, relatively higher is the roughage content. When they go into a feedlot here in the United States, the feedlot diet has 80 to 90% concentrate and 10 to 20% roughage. As a result, those animals don't belch much. That means if you compare a grass-finished animal here in the United States to a corn-finished animal in a feedlot, then this corn-finished animal will not have a higher, but actually a lower carbon footprint, even if you account for the fact that the grass-finished animal is on pasture and pasture sequester carbon. And even if you account for the fact that the feedlot, of course, imports feed from corn-growing regions, for example, and this corn growing has an environmental footprint and the transportation has a footprint and so on. If you compare the life cycle of the one system versus the other, then it might surprise some that the feedlot does not look worse. In many cases, it looks better. But that's, that's a life cycle assessment derived answer that I can give you. And there are publications on this.
Our colleague Rok Mihalic asked or wrote on chat, people were misled by politicians who believed in the GVP 100 model and therefore designed policies that considered animal agriculture as one of the causes of global warming. Can your findings change current EU policy?
So
are politicians listening to you?
Yeah, so I wouldn't go as far as saying that politicians misled the public, because you have to understand, we are academicians, right? So I'm talking to people at the University of Ljubljana. So you're a scientist, I'm a scientist, and we as scientists have to wrap our mind around some very complex issues that we discussed today. We're just talking about one gas today, right? One gas today. Some people say it's the worst thing in the world, and other people say, no, this can be a problem, but it can also be a solution if we reduce it. Methane does not have to be a problem. It can be a solution to climate change if we manage it. If we don't manage it, it will be a problem. So I think this notion, and that's my notion, that methane is only a problem if we ignore it, if we don't manage it, that is now really appreciated. When I go talk to policymakers in Finland or in Ireland or in Scotland or in New Zealand or in Australia, then they're actually very receptive to that because they don't want to get rid of their farmers. They need farmers. They all understand that. If you tell them that if they work with farmers to reduce emissions, that they can be part of a climate solution, then you change the way they think about farming. And I think this is really important. We do not want to downplay the importance of livestock-related greenhouse gases. I'm not downplaying that at all, but I'm saying give farmers the tools to reduce emissions because then they can be part of a climate solution. And, and I have seen that really making a difference. I've seen it in Ireland. I think I will see it in Australia and New Zealand in the next few weeks when I travel there. I have seen this here in California. I think we are changing first the minds of our farmers right now, because our farmers in the past said, we are not part of the problem. This is ridiculous. Leave us alone. Well, that's not true, because methane can be a problem unless you manage it. And then it can be a solution. I'll give you one analogy. And I know I'm giving long answers here, but I think it's important for everybody to understand that. Imagine it being winter right now, and your kids open the windows and doors of your house in the middle of winter. Then you would tell your kids, what are you doing? You let all this heat go out of the house. This is you burning money, right? So if we don't manage methane, we are doing the same thing. Because about 10% of the energy we feed to our animals gets lost as enteric methane. And more methane gets lost from the manure storages. That's a loss of methane. It's a loss of energy, and it's a loss of money. Don't we want to manage that? Of course we do. We do want to manage that, because when we do, not just do we save money, but we also reduce emissions that affect our climate. So that is the direction I'm coming from, and it is a direction that many politicians are listening to and incorporate. They're not trying to go to universities like yours asking, what do you think of this? And then the question is, how will you answer? I hope that those of you who work on greenhouse gases from livestock, that you look into this issue. There's now a lot of literature on this GWP star. There's literature on the biogenic carbon cycle, and so forth. And when people ask you, that you will give your opinion. But you also have to be prepared that if you do give your opinion, that you will be criticized by those extremists out there, which are out there in large numbers. Okay, and I have received that criticism myself, but I'm not afraid of it, because to me, it is a high honor to serve our food sector, particularly the farming sector, and help them be the best environmental patron they can be. And I think that's really our role in society, for us as academicians, to help those that need to do fact-based practices. And so, yeah, so I have actually good experiences. I'm quite concerned about a lot of the EU policy. For example, the EU policy on nitrogen. You might have seen what's going on in Europe, in the Netherlands right now, where the Dutch government, and now hear this, where the Dutch government wants to get rid of about 1/3 of nitrogen emissions. And they want to achieve this by getting rid of 1/3 of their livestock producers. And the Dutch government has taken 25 billion, that's with a B, billion euros, and they said we use these 25 billion euros to buy farmers out of farming. And they are telling a farmer, if you sign this line and we give you money for your farm, then you sign that you will never be a farmer again, and neither will your children. And I am just very disappointed to hear this kind of language from a government in Europe. See, there's a hand up there.
Dr. Jože Verbič from Agriculture Institute has a question. Jože, please.
In fact, I have a comment to a suggestion given by Frank. In fact, for Slovenia, we do have a comparison of GVP 100 and GVP star. So the results show that according to GVP 100, the contribution of livestock to total greenhouse gas emissions is about 8%. And by introducing of GVP star, the contribution of livestock drops to 1.2%. So thank you very much for your explanations on this. We will trust even more now that we are on the right way to calculate our emissions.
Yes, and thank you for this comment. What's really important is that the IPCC, if I may go back to this slide, that they now agree with our criticism, that they say, yes, the criticism is correct. GWP 100 overblows the impact of constant sources of methane on warming by a factor of 3 to 4. They are saying it now. It's not just a bunch of agricultural researchers. It's the Intergovernmental Panel of Climate Change, the world's leading body on climate, saying it. So to me, this is really important. As I said during my talk, I don't think that we can get rid of GWP 100 because the world has been using it for 30 years. This is like turning a super tanker, okay? It takes a while to turn this ship, but eventually it will turn. Eventually it will turn. And this will be very much positive in how it will guide our farmers to do what's right for the climate.
Jože, do you have more questions or comments?
Not really. Again, comment. Okay, IPCC somehow knows that there are new metrics. However, we have to follow the manuals of IPCC. The last one was issued in 2019, the one before in 2006. So I'm afraid that we will wait another 10 years for a new manual from IPCC for reporting. I see the problem there.
Well, the IPCC has actually as a policy that you don't have to stick to GWP 100. You can use GWP star today under IPCC guidelines, but you as a country have to declare that that's what you're doing and why you're doing it. You will see on this page here, the one that I'm showing. Can you still see this page?
Yeah.
So you see here the mentioning of GWP star above what I highlighted. You see it throughout the page, right? See it in numerous places. You see GWP star cited. This chapter 7 in this IPCC AR6 report has very clearly stated that GWP star is a scientific assessment of the impact methane has on warming that's superior over others, and that describes the rate of change over time that a source has that produces methane. And I think that's really what we want to know. We want to know what is the rate of change between, let's say, the years 1980 versus 2000 versus 2020 versus the year 2040. Because if you want to know what the warming impact is, then you're comparing one time point to another, because that's what warming or cooling means, that you look at, are the temperatures going up? That's warming. Or are they constant? Or are they going down over time? That's cooling. And GWP 100 doesn't give you that information. GWP star does. I think we all have to push hard, and the Irish are doing it, and the Scottish are doing it, and if you do it and you talk to your colleagues throughout the rest of Europe, then things will change. It always starts with people like you and I.
We have today also people from Ministry of Agriculture, so I hope that they will bring this message to the policymakers. We have farmers with us and students, and I saw that also our Vice Dean is with us, so I would ask Tatiana to say some words. Tatiana?
It was not my intention to say some words today or this night.
I didn't see you on the beginning, so Tatiana, sorry.
No, I have problems at the beginning. I just come to the lecture 10 minutes later. I didn't hear the beginning, so it's okay. Thank you, Professor Frank Mitchell, for a really good lecture. I think that we all learn a lot now about the methane emission, and also thank you, Maria, bring this professor to have a lecture for us, even that we have some problems last week, but thank you again that you managed to have a lecture for us.
Well, you're very welcome from my end, and I would be so happy to come and visit you in your beautiful country. It has been too long since the last time I was there, 30 years. And so I know many things have changed since. You are a very special country to me because I have seen it when it was part of Yugoslavia, and then I have once seen it after. And the path that you have gone has been so successful, and I would love to see it again. So I hope it's in the future that we meet in person.
Yeah, you are warmly welcome. Then we will organize face-to-face workshop.
Yeah,
meeting.
I'd be glad to do this. I'm doing it next week in Australia. I'm going from there to New Zealand. This is a very international issue. Okay, people all over the world want to know which direction is this going. What does it mean to livestock producers? What does it mean to policymakers and so on? So you're not alone. Everybody is learning about it. People are adjusting, and it is a very interesting debate, and I'm glad to be in the midst of it.
Professor, I have also one question or comments. Is this enough for this planet that only Europe and North America work on these issues?
No.
Because on the another side, you can see that population size of cattle in Brazil increased a lot, and also I think India and Russia.
Yeah, as I said,
we have today also some colleagues from Ukraine, so I would like to welcome my colleagues from Ukrainian universities. I invited them, so I would like to hear your opinion. What can
So first of all, my warmest wishes to those colleagues in Ukraine. Our hearts are with you. Just want you to know that. 70 to 80% of all the emissions that livestock produce globally, 70 to 80%, so the vast majority, develop in so-called developing countries of the third world. And here India is particularly important. I told you the United States has 9 million dairy cows. 9. How much does Slovenia have dairy cows?
We have less than 100,000.
100,000.
Yeah.
India
97,000 dairy cows, and then we have additional 60 or 65,000 suckler cows. It means cows feed calves.
So so that's how many you have. We have 9 million here in the United States. India has 300 million. 300 million. Okay, but the vast majority of these 300 million produce very, very, very little milk. So in countries like, and once they stop milking, once they stop lactating, they're just cut loose and they're free to go. Okay, so they're no longer producing milk, but they cannot be slaughtered for religious reasons. So they live and breathe and excrete, but they don't produce. And that has a devastating impact on the livestock impact of that country. In many African countries, and please don't take this as me bashing developing countries. I do the opposite. I work with these countries to improve their environmental performance. But I want to speak to your question. In many African countries, livestock is not raised primarily for food. So let's say a tribe or a family does not have a herd of cattle to eat them as soon as these animals are mature, but they have other functions, such as they are retirement how shall we call that? So they're like a retirement insurance or a social security insurance. If you want to marry your daughter off, then you have to have cattle to go with it, and so on. So they have currency function and so on. So in those countries, cattle are left alive however long they biologically can. So they slaughter them when they're 10 or 15 or 20 years old. And when they fall over of old age, then they are being eaten. They're not eaten after 2 or 3 or 4 years, but when they no longer can live. It's a very different type of producing livestock in many of these countries. And because of that, the livestock numbers are massive. They are very large. So the lion's share of livestock emissions globally occurs in developing countries. And we need to work with these developing countries to reduce those emissions, and we can.
Thank you. Do you have some other questions? We have people also from Extension Service.
I see
If
there's
some
another
advisor-
one. I've seen another one in the
Yeah.
chat.
Alesh Fister.
Yeah, so this is a good question.
Does your explanation of grazing versus feedlot already takes into account methane being flow gas?
Yes, so both grazing animals and feedlot finished animals eat plants, right? And in the one case, they eat it while these plants are alive. In the other case, after they were harvested. The difference between the feedlot diet and the feedlot finished animals and the grazing animals is that in order to produce the crops that the feedlot finished animals eat, you need to use some fossil fuels for fertilizers. That's the big difference. But the feedlot finished animals, they live about almost half the lifespan of their grass-finished peers. And the grass-finished peers eat a diet throughout their entire life that is a majority of roughage. So it's ideal for methanogens, these microbes that produce methane, because that is what they need to strive. The methanogens really only eat roughage. That's the only thing that they need. They don't like concentrate. They cannot do anything with corn or so. They need roughage. And so if you do the math, the accounting of the one versus the other, then they're either similar or in many cases, the feedlot finished system ranks higher, meaning better. That's not to say that I say, Frank Mittlener says, we should all have feedlots and this is the better way than grazing. I think there's a place for both. Here in the United States, the grass finished products, so if you have only grass production, those products don't sell as good as the feedlot finished products. And the reason is that the feedlot finished products, the feedlot finished beef is much younger when it goes to slaughter. And that means the meat is much more tender. But the animals are already fully mature. They have already a fully mature marbling. The intramuscular fat is pretty much ideal. And the quality of the fat, of this intramuscular fat, has a particular taste that speaks to the American palate. If you were to come here and I were to take you to a steakhouse and we were to try a grass-finished versus a corn-finished steak, I can guarantee you that you would say, this is an incredible meat quality. I know in Europe, they oftentimes look at a feedlot and say, oh my gosh, look how terrible. But I guarantee you that if you were to eat the product, you would approve of the product. I can guarantee you that. I come from Europe. I've eaten beef all over the world. I can tell you, this is some excellent product.
Alesh Fister wrote that, thank you for explanation. It's a little clearer now.
Yeah, the biogenic carbon cycle and so on. This is all very abstract, but I showed it really to show you why the one side is a relatively short-lived cycle, and that's the cow. Whereas on the fossil fuel side, it's not a short-lived cycle. Any kind of greenhouse gases that are associated with the burning of oil, coal, and gas are new additional carbon added to the atmosphere. And this is totally different. I'm really tired of people comparing cows versus cars. They shouldn't be compared because they are totally different emission sources. The one is a new addition of carbon to the atmosphere, causing additional warming, and that's the car, and the cow is not. And so we need to make people understand that. That's a totally different story.
But in fact, it's a problem that society doesn't listen us. They don't want to hear our explanation.
Well,
Even if we have scientific base.
Well, this is, it is difficult, okay? I have to tell you this is difficult, and I know it's difficult because I keep breaking this down and explaining this to school classes, to politicians, to journalists, and so on. It takes a while to explain it. If you go to the Clear Center webpage, my webpage, you'll find many ways we explain it. We have pieces called explainers that explain what's soil carbon sequestration or how do cows affect the climate and so on. So we have explainers, we have blogs. These are longer write-ups of complicated things that we break down. We have making it our hallmark at the Clear Center in my department here to explain this stuff in ways people can understand. Because unfortunately, the majority of scientists in the world doesn't do that. They do complicated research and publish it in technical journals, but the public will never understand what that says. Never. And I think we all know what I'm saying here. That's the truth, right? The vast majority of people do this in academia. I also do this, but that's not all I do. My main intent is to have real-world impact. Impact to our farmers, impact to the people consuming the food our farmers produce, impact with policymakers and so on. And I think we all need to do more of that.
Thank you very much. Do we have some other questions?
It's almost bedtime where you are, huh?
It's nearly 10 o'clock for us, yeah.
There you go.
If there's no question, then I would like to say thank you very much, Professor Frank Mitleuner, and please come to visit us this summer or as soon as possible. When you came back from Australia and New Zealand,
I'd be very honored. I'd be very honored. And next Europe trip, maybe I can shoot you an email, and maybe we can arrange for something. That would be really my pleasure. Yeah.
Warmly welcome. So thank you very much. I will contact you via email, and thanks a lot for your time and for this to share your experiences, your knowledge with us. We are
You're welcome.
Very, very thankful. Thanks a lot.
You're very welcome.
Have a nice trip to Australia and New Zealand.
Thank you. Bye-bye.
Bye.